In this exercise, we consider a small mass M which is suspended by means of two wires in the middle of the street. The street width is L and the thread tension, wire's tension, is P and maximum thread tension is P. The height of the mass with respect to the ground is H. So our origin, I will fix the ground, and I'm looking for the height of the fixation of these wires as respect to the ground. So we know L, P, little h, M, and we are looking for H, big H. So, with respect to the ground, this height is equal to a small h plus some distance, some height, x, which I will draw here. So, and now we will find this distance x. Our mass, our system of study, is this little mass. It's the first step in all static exercises. We need to choose our system. So our system is a small mass M. And on the second step, we need to present all the external forces as respect to our system, to our mass M. So we have weight P, the gravity, and we have two thread tensions that I will present. It will be small p, P1 and P2. And the direction of these forces is always from the system toward the wire, toward the fixation. So we have three forces. The system is in static equilibrium. It means that the sum of all forces equal 0. Sum of all external forces equal 0. And now I will write, so the gravity Pm plus 2 thread tensions equals 0. The third step, I need to fix the coordinate system, and I will introduce the rectangular coordinate system x, y, and now I will present all the vectors in this coordinate system. So the first vector is the gravity force, Pm. The direction of this vector is opposite to the chosen coordinate y. So the unit vector minus Ey will show the direction of our gravity force times mg. The second force is a thread tension, and now I will decompose this thread tension into two vectors. The first one with x direction and the second one with y direction. And I will introduce also the angle alpha. So the angle alpha is here, and now I will decompose the thread tension into two vectors. The first one has a direction minus Ex, opposite to the direction of x, and I will project, so P cos alpha. The second vector has a direction of Ey, and p sin alpha. And now I can start to write my equation. So the gravity force equal min Ey mg. And now I didn't do, and I will do it now. I will present my second thread tension. So I will write P1 and P2. This second vector is here. So I will project it on the axis X and Y. So we have to introduce also on the angle alpha. So here is the angle alpha. The same angle alpha is here. And I will decompose my thread tension vector into two vectors with x direction, Ex, P cos alpha plus P sin alpha Ey. So the same. And now I will put it into the equation and I will have minus Ex P cos alpha plus Ey P sin alpha plus Ex P cos alpha plus P sin Ey alpha equals 0. So the two terms Ex P cos alpha and minus Ex P cos alpha will disappear, and I will have only the terms with Ey direction. So I can write minus mg plus 2 times P sinus alpha equals 0. And I can find now the angle alpha. So sin alpha equal mg divided by 2p. Well, and now I will calculate x. So I can present x over L by 2, so x divided by 1/2 of L equal as tangent alpha. This y tangent is sinus alpha divided by cosinus alpha, and x equal L times sinus alpha divided by 2 cosinus alpha. So sinus alpha I have already found, and now I will find cos alpha is the square root of 1 minus sin square alpha equal square root of 1 minus mg square divided by 4p square. I will present it as 1 divided by 2p square root of 4p square minus m square g square. And now I can calculate x. It will be 1/2 of L mg divided by 2p multiplied by 2p and divided by square root of 4p square minus m square g square. So 2p and 2p will disappear, and I have x equal L divided by 2 mg divided by the square root of 4p square minus m square g square. And the height of fixation is equal little h plus x. So L divided by 2 mg square root 4p square minus m square g square. So we have found our h.